Here's a reaction with a weak base ammonia, 0.010 molar ammonia, Kb 1.8 times 10 to the minus 5. Let's find the pH. Okay, this problem is similar to the last one, except that pH from hydroxide is a little different than pH from hydronium, but same things. So what you do in this problem is set up the ice table. We're starting with 0.010 molar ammonia and no ammonium or hydroxide. So at equilibrium, you'll have minus X for ammonia and the 0.010, while X will equal ammonium and the hydroxide value. Kb for this expression, 1.8 times 10 to the minus 5. Ks are always products over reactants, so that would be ammonium times hydroxide over ammonia. That would be X times X, or X squared, divided by 0.01 minus X, all right? And once again, this is the complete expression, but you can probably imagine that we'll check it here and see if we can do an approximation where we can remove that little minus X by the 0.010. So just like with the acids, you can check the bases too. If 100 times Kb is less than Cb, you can ignore that little minus X. So 100 times 1.8 times 10 to the minus 5, the Kb, is 1.8 times 10 to the minus 3. And that number is less than Cb, 0.010, which is 1.0 times 10 to the minus 2. Now, Cb and 100 times Kb are getting closer to each other. However, 100 times K is still less than C, so you are welcome to get rid of that minus X. So if you do that, then X squared equals Kb times Cb. X squared equals 1.8 10 to the minus 5 times 0.010. So the square root of both sides, it gives you just X, which is hydroxide. Square root of Kb times Cb comes out to be 4.2 times 10 to the minus 4. And that equals the concentration of hydroxide and the concentration of ammonium, which is pretty cool. We assume that ammonia stays the same at 0.010 moles per liter. Now, you can kind of check yourself with these approximations. So if the original concentration minus the amount that you calculate, hydroxide or hydronium, is about the same as the original concentration, then you're good to go. And this one is pretty close to 0.01, so it's okay. And like before on the quadratic, you can solve these kind of questions. I did that below. And you can see how X came out to be 0.00042, or 4.2 times 10 to the minus 4. And the other X value is negative, and that just doesn't fly. So everything seems to be pretty good here, and we are good to go. Okay, so on the last slide, we figured out the hydroxide is 4.2 times 10 to the minus 4 moles per liter, and that is pretty cool unto itself. However, we want to calculate the pH. And again, in this problem, we're starting with hydroxide, not hydronium, so we need to somehow translate hydroxide to hydronium to find the pH. Now, what I would probably do is I would find POH first, and that's just equal to minus log of the hydroxide. So minus log 4.2 times 10 to the minus 4 gives you 3.37. That's POH. So pH plus POH equals 14, which is what we saw earlier. So 14 minus 3.37, 10.63, and we are good to go. A lot of times, I like to use this expression. So just like with the weak acid, we saw that pH equals minus log square root Ka times Ca, as long as 100 times K is less than C. Well, for weak bases, 14 plus log square root Kb times Cb is actually a pretty nice approximation as well. So instead of going like hydroxide to POH to pH or something like that, or hydroxide to hydronium and then pH, which would have worked fine too, you can do it all in one step. So I do recommend checking out these short and quick and dirty kind of versions of these equations, but of course it's up to you. This is an overview of the 4 equations that I use for strong acids and strong bases. Now, strong acids and strong bases dissociate 100%. So when you have like 0.1 molar HNO3, that means 0.1 molar hydronium. So for those, the pH is literally minus log the concentration of the acid, or minus log hydronium. For strong bases, because that hydroxide term, you go 14 equals pH plus POH, and you can solve it from there. So 14 plus log concentration of the base will equal the pH. So again, there's no Kas or Kbs for strong acids and strong bases. We only worry about those down below when we get to weak systems. Now for weak systems, assuming 100 times K is less than C, pH equals minus log square root Ka times Ca. And for weak bases, it would be pH equals 14 plus log square root Kb times Cb. And again, these four equations help me out a lot. That's why I'm sharing them with you. I encourage you to memorize them so you don't have to think about it too much. Good to go.